Hello students, we're back in here to 1.5 because in this section we're going to talk about sums and products and quotients of complex numbers. So last class we looked a little bit at the idea that if we have the product of a complex number, then the argument is the sum of the two arguments. So let's look at some proof of that. So if we look at some complex number, let's let z be a plus bi, and then we could have w be c plus di. So we could say that arg z is tan inverse of b over a, and we could call that theta, like above. With w, we could do the same thing. So I'm just going to skip ahead and say that arg w is equal to tan inverse of d over c. And let's find zw. So that's going to be ac minus bd for my real components, plus my imaginary components are going to be bc plus ad I. All right, so my argument is going to be tan inverse of BC plus AD over AC minus BD. But if I think about the sum of theta and phi, so if I think about theta plus phi, and then if I think about doing tan of theta plus phi, and of course I'm thinking of tan because this is all built on tan inverses. So tan of theta plus phi is going to be tan theta plus tan phi over 1 minus tan theta tan phi. Well, that's going to be equal to, so tangent of this angle would be b over a plus d over c over 1 minus that product. So if I multiply top bottom by ac, the a's are going to cancel, so I'll get bc, c's will cancel, I'll get da over ac minus bd. But of course, that is the argument of this. So now I've proven that if I have the product of complex numbers, the argument will be the sum of the separate arguments. Let's look at the magnitudes. So magnitude z is going to be a squared plus b squared. Magnitude w is going to be c squared plus d squared. And then magnitude of the product is going to be square root of ac minus bd squared plus bc plus ad squared. Well, if I expand this and simplify it, I'm going to get a squared c squared minus 2abcd plus b squared d squared plus, expanding this, b squared c squared 2abcd plus a squared d squared, and of course square root of all of that. So if I simplify, I'm going to end up with a squared c squared plus a squared d squared. So I'll factor out a squared, c squared plus d squared, plus b squared, I can do the same thing, c squared plus d squared. But of course that's the same as, ending up with square root, square root of, a squared plus b squared times c squared plus d squared, which is then the magnitude of z times w. So similar to my angle properties, I also have modulus properties. So if I have r cis theta times k cis phi, then I end up with rk cis theta plus phi. Similarly, if I divide, I end up dividing my modulus values, and you could prove that similar to how we proved the other ones.